Hello everyone, my name is Anthony Shivkumar, and in today's video I'm going to be talking about something called as high performance computing, or HPC as they call it. Now, in one of the work that I was doing, I was trying to parse all the data for an AI application, and when I was trying to run the parsing of the data, normalizing of the data, creating chunks, creating embeddings, which is all part of creating a RAG system in an AI application, to say the least, it was starting to take a lot of time. And while I was trying to figure out how to optimize this was running on a Python application at a high level on a Jupyter notebook. I didn't expect it to take that much time, but it was very slow. And then parsing all of these documents and trying to get and create the embeddings and making sure it worked on the AI system, the pre-processing was very slow. So in order for me to speed up that system, or to hopefully do the pre-processing of the data at a much faster speed, I started to investigate onto something called as the high performance compute and what exactly it is all about. In a nutshell, high performance compute means computing things that require high performance. And there are a lot of things required when you're dealing with high performance compute. So in a nutshell, if you have multiple computers and you want to utilize all the compute power that you have to process this one little application, in terms of, in my particular case, was data cleaning or data pre-processing, how do you organize all of the cores, all of the CPUs that you have, or in many cases GPUs or accelerators or even FPGAs, so that you can utilize all those resources to distribute the compute across all of these systems, so that you can perform your task faster. And that's where the whole realization of high performance compute came to me. Instead of using one single core, one single thread, and running this Jupyter notebook application for pre-processing, which is too slow, there has to be a better way to distribute the compute load. And I started to develop this application. I wrote this whole thing in C, which I'll be talking about, and I'll share a little bit about how I did it. But the concept right now is now moving from a single threaded mindset all the way into how you can design your application for multiple cores, multiple threads, multiple sockets. You got to think of how you can write software for parallel programming. And this also is kind of the mindset when you're doing GPU programming or CUDA programming or OpenCL programming, is how do you distribute the workloads across multiple kernels or multiple threads in a GPU setting. So let's get started. I'll just show you an architecture overview of what are all the different components that are required when it comes to HPC. And in a nutshell, even within that one socket or one CPU, for example, if I'm using the Xeon processors, it has multiple cores, and each core has, say, 2 threads. So you have multi-threaded environment, and then which is basically if each core, say you have 10 cores and each core has, say, 2 threads, they call it hyper-threading in that sense. So that means you technically have like 20 cores, though there is some subtleties between what makes the differences. For example, the L1, L2 cache will be shared across those 2 threads for that one core, and the L3 cache will most likely be shared across the whole CPU. So there are certain differences between the threads and cores, but in a nutshell, they all can be parallel processed. Another thing that you could do is you could leverage certain instruction sets from the application itself. So if you're doing matrix multiplication, or you're doing some form of string manipulation, some of the Xeon processors has this extension called the AVX512 or the AVX2 if it's on my laptop. So all the core processors have the AVX2 instruction sets, but a lot of the Xeon new processors have the AVX512, and the latest 4th generation and 5th generation also have the AMX, which is the advanced matrix extension instruction set. And all these things, and the AVX is the advanced vector extension instruction set. And all of these instructions can allow you to parallel process at the instruction level set, at the register level set. So in a high performance compute environment, you really want to take all the building blocks of what all you can parallel process and add that from at the register level, add that at the core level or at the multi-thread level, and then add that between sockets or between CPUs. Many Xeon processors have on the motherboard you have 2 CPUs on one motherboard, so it's dual socket motherboards. And then how do you scale that across multiple clusters? So that's the kind of mindset in programming, or the paradigm shift in programming, when you're dealing with high performance compute. Every single layer of that whole stack you could hyper optimize, and when you do that, you can get significant amount of speed. So in a nutshell, what took us 10 days to pre-process took seconds to do this on a Xeon processor with dual sockets with high performance computing in mind. But it was not easy to get this set up because we wrote this in low level C. You can write this in C++. We used the Intel 1 API for doing this. Intel 1 API, which is their code for you to compile all of this stuff onto their platform. So by leveraging all of the low-level stuff, you can get very high performance. So let's get started, and I'll show you the architecture of how things work. And from there, we start to look at the code and break down each piece by piece to get a deeper understanding of what's going on. So in the HPC system architecture, the idea is to aggregate all the computing power to deliver the high performance. And our goal is to efficiently solve the complex problems which are compute intensive, by leveraging the parallelism and the optimization techniques. So in here, what I have are two documents. For example, say these are the laws, and each one of these is one cluster. So this particular system over here is running on one Xeon processor, and this application over here is running on another Xeon processor. And this is a dual socket CPU. So you have one socket over here, one socket here in one motherboard. So many Xeon and many server grade systems will have this dual socket architecture. So in a nutshell, what's happening is I am taking this document and I am trying to parse it through this one CPU, CPU1. And each CPU will have their own set of RAMs, or DRAM, which is dynamic read access memory, and there is something called as NUMA. NUMA is non-uniform memory access affinity, and we want to make sure that if you're running the application on this CPU, we want to allow all the data to be stored in this RAM, because if we store it in this RAM and we're trying to process and your application running on this CPU, there is going to be some delay. And since we're dealing with high performance compute, we want to optimize for every single latency that's possible in your application. So it's a very simple command where you tell, these are my NUMA nodes, and I would like to, assign my application, and I want to store all the files in this DRAM over here. So the first thing first, we want to take all the data and copy to DRAM, but we want to copy to a very specific DRAM, in this particular case, the NUMA affinity. And once we load all the files, we then try to parallelize it, because the compute is going to parse all the data, create the chunks, create the embeddings, and so on and so forth. So in here, what I'm trying to do is now this Xeon processor that we have has, I think, a total of 16 cores. And this also has 16 cores. So we have a total of 32 cores in this whole motherboard over here. And we can say that now that we have divided the data itself from action regulation, they're very similar, so it doesn't matter. They're not like one is bigger than the other. They're all both approximately 100 MB of data, but the parsing has a lot to do with the string manipulation, string normalization. That's taking a lot of time. And each of these files and each one of these things might be around 600 files, and some of them might be 1,000 files, but the total processing of each will be approximately the same. And here we're saying that each file now can be divided into different cores. So if we have like 1, 2, 3, 4, 5, 6 or 4 over here, we can say one XML file is going to be for one XML file. You load each one XML file to each core and let each core process one XML file. So we're parallel processing in this particular context. Now there are many ways of designing the HPC architecture, but for this application, I'm trying to process one file in one core. And we're doing a dynamic load balancing in here. So if one core finishes the work, then it picks up the next file in the queue. And this can be done through OpenMP, and I'll show you the code shortly how all of this works. So in a high level overview, we're basically dividing the files into different cores, and in each core we are now parsing the XML data by sections, and here we're using an instruction set called single instruction multiple data. And single instruction multiple data is, in this particular context, we're using the AVX512, and we want to clean up the strings. So if I have a string of say A, B, and C, for example, and it has a lot of these \n characters and \n. I want to remove all of these unwanted characters and just keep the characters very clean. And single instruction multiple data can allow us to do this by matching each one of these letters. However the document is going character by character. It's matching whether there is any unwanted characters. So you could have, say, I want to match every letter with \n, and if there is a match, we delete it, and if there is no match, so in this case there was a match, we delete it, and if there's no match, you keep the original string. That way we can normalize it, and we can do, and there's 32 registers on this particular platform, so we can technically do around 2.1 kilobytes of data, which is around 2.1 kilobits of letters, because each letter is technically 1 byte. And that's how fast you can do, and this is happening at 3 gigahertz. That's the speed of the system. So you can, ideally you're not getting the full 3 gigahertz because there's an operating system running, there's Kubernetes running, there's other applications running, but nevertheless, if you remove all the other stuff, you can think of parallel processing and processing all of this at very, very high speeds, because you're parallel processing in each core using these instruction sets to do the string manipulation, string cleanup. And then there are other things where you take all the string and then you create the embeddings and then you store it in the database. So that's the high level overview of what's happening. Now there are a few things that you notice. If you want to spawn them between different CPUs or you want to scale them to completely different computers, you have to use something called the MPI, which I'm using is called a message passing interface. And this is a command, it's a open standard that allows you to distribute the workload across multiple cores. You can distribute it across multiple cores, but you technically would just use OpenMP. But between multiple CPUs, it starts to become a much better way to use MPI. You could also not necessarily use MPI, and you can use OpenMP even between two sockets. But I found that using MPI allows me to scale across the whole system, because now I can have one core, processing one set of data, the other core, one socket or one CPU processing one set of data, the other CPU having one set of data. So I rather have the control at the MPI layer than just putting all the loads across the CPUs. I just made the design a little bit more cleaner from my perspective, but someone might say, why would you want to have MPI at per mother, per socket or per node? But in this particular design, I've used MPI to distribute the compute between each of the Xeon processors. So let's have a look at the details of every one of these things which I talked about, what MPI is, what dual socket system is, what NUMA nodes are, what OpenMP can do, and what the instruction sets is all about. Now, the system that we have has the Xeon processors on 2 Xeon processors per motherboard, as we mentioned earlier. And MPI is a message passing protocol or message passing interface that allows me to distribute the workload across different, nodes, different computers, different systems. But in this particular case, I am trying to distribute between two of the CPUs, CPU 1 and this is CPU 2. And in a command line, there's something called as MPI Run. You can use MPI CC to compile the program, and then you do MPI Run to run the program. And in here, I will say something like in nodes, I would like to run 2 processes. So you're technically running 2 processes. It's called an NP command, which is called the number of processes. You put number 2 processes, then you put in some parameters that you want, the arguments, and then it'll run. So technically, this is your command for running the 2 processes, and then if you have it distributed across multiple networks, then you might probably want to put which network which CPU is running on. So there are other parameters that you might want to put, especially when it's distributed across a network or completely different areas. So that's pretty much it when you want to run an MPI program. And in your program, you would have certain parameters that talk about what rank they are in. So for example, you could have in the code saying that if I'm in rank 1, so an MPI in the program itself, it starts from rank 0, so this will be rank 0, this will be rank 1, depending on how everything is distributed. And you can say if you're rank 0, I want to process all the acts. If I'm in rank 1, I want to process all the regulations. And each rank is technically one different process. So it's 1 process, 2 process, all running through the MPI system, and generally one of them will be the master process. And if you're communicating between these, you generally use something called as collective communications, which is a method of communicating between MPI processes. There's all reduce, there's scatter reduce, and there's many different protocols of how you can do the communication. And then you can say in each process, I want to compute this particular set of data set, this particular data set, and then at the end you can accumulate the data into one of the processes that says, okay, after the end of it, I want you to send me all the data in terms of how long you took, or if you're doing a back propagation, give me all the weights, so I will calculate all the updated weights, and vice versa. So that's how MPI kind of runs. We'll go more into the code shortly, but that's in a nutshell what MPI does. It distributes the load of it basically spawns the number of processes you want, and it'll spawn them in the location that you want, whether it's at the same motherboard with two different CPUs or across the network. In the previous slide, we talked about MPI, and in this slide, we're talking about NUMA nodes. Now, when you have two dual sockets on the same motherboard, you might have DRAM that's associated with each of the CPUs. And if you're running a program that's, say, in this CPU, and all the memory is distributed across this memory over here and this memory over here, there's good chances that when I'm fetching data from this memory, it can be very fast. And when I'm fetching data from this memory, it might be pretty slow, because it's going to go through a quick path interconnect that's going to go through another bus, and there's going to be a latency with speed. And because the speed between this memory over here that's associated with CPU 1 and the memory that's associated with CPU 2 is different, we call them non-uniform memory access. And that's what NUMA stands for, because the speed where your data stored in memory is different, and as a result the speed is a difference. It's not uniform, so you call them non-uniform memory access. And one way to make this system much more robust is, especially when you're dealing with high performance compute, is saying that in this particular case, say we are dealing with data 1 and this is dealing with data 2, and if I have one MPI process running over here and the other MPI process over here, I want to make sure that everything in this process is only storing data in this RAM over here, DRAM, and I want everything running on this process to store data in DRAM over here. So if you have a hard drive and you're basically trying to load all the data using, say, malloc, and you're trying to copy the data from DRAM to your heap memory over here, and your heap memory is generally in your DRAM, you want to say, I want everything to go, if I'm in CPU 1 and program 1, I want everything to be loaded in this DRAM, and for this CPU, I want everything stored in this DRAM. This will allow us, when the program is then running, that the speed at which it is computing all of this will be much faster, rather than taking taking data from different memory where the speed can be it's unpredictable, because it's taking at it will be non-uniform. So that's what NUMA is. So when you're dealing with a dual socket architecture, when you're dealing with high performance compute, all of these details do matter, because you're dealing with high performance compute. The next layer of optimization is OpenMP. Now, in the previous slide, I had mentioned that in your CPU core, if this is your CPU, you might have multiple cores and threads, and you want one of the data to basically process on one CPU core and the other data to be processed on another CPU core, and you want to distribute the whole system, distribute the data across all the cores available in your system, and do a dynamic load balancing. So the way you do that is using OpenMP. Now, if your data is very similar and the computation is very similar, if the computation is very similar but the data varies, so you technically, and they're not very much interrelated to each other. So if I'm processing one data over here and I store in the database, the other data here in the database, and there's very much need for them data 1 communicating with data 2 is not necessary. They're just doing their own thing, but they need the computation to do all of this stuff. I can parallelize it through OpenMP, and I can use something called as a dynamic allocation, which will do the load balancing for us, knowing that if one CPU core finishes the data, it will just take the next data in the queue. And all of this can be done using the Pragma OMP parallel for. It says, please parallelize this for loop, and here you would have something called as dynamic, which will now do the dynamic load balancing. Now, this only works if if you're doing something that's iterative and it's just purely computation. If you're doing, and these are generally called, like data parallelism. But if you're doing something such as task parallelism, and task parallelism would be something like your server, where you have, one thread listening for certain connections and the other thread doing some form of worker information. So this is not particularly a very a consistent way of processing data. They're two different tasks, and in here you probably may not be able to use OpenMP. You might have to use something such as pthreads, which is also a form of parallelism, but it's not doing at the data level, it's doing at the task level, and each task is doing completely different things. It's a different software, different code. I wouldn't say different software, but different, it's doing a different task altogether. So if you're just purely dealing with data and the computation is exactly the same, just the data changes, OpenMP is really an easy way to set up parallel processing. And then the last part of parallel processing that you could do to optimize your code is Intrinsics. Now, Intrinsics has got a one-to-one mapping with the instruction set of your processor. Now, Intel has something called the AVX512, which is nothing but 512 bits, which is approximately 64 bytes. Actually, not approximately, it is 64 bytes of data. And in characters or with string, one character, one char is equals to 1 byte. So technically you can process 64 bytes, and they have 32 registers of this. So technically you can have 64 bytes into 32 registers, which is approximately around 2 point something kilobits of data, or in this particular case 2 point something letters that I can process at the same time. So what exactly is Intrinsics and what is it? It's known as single instruction multiple data. Single instruction multiple data is, in this particular case, the instruction is addition. In this particular case, the instruction is addition, but the data can change. So, for example, if I'm matching, say, the word character, and I'm trying to see whether it's equal to, say, \n. So the data is, say, in this particular case, data 1 is C, and this could be, say I have a letter, the word called child, CHILD, and I'm trying to compare whether they all are compared to \n, because I am trying to clean up and sanitize my data, trim the data. I can process this very quickly, and this is the same instruction. It's all compare and equal to, but the data is different. So in one register I can do 64 of these, and in the system we have per core or per thread we have 32 registers, so I can technically do 64 into 32, and each core or each thread has this, so that means each thread can do 64, but I'm only processing one file in each core. So technically speaking, I can only do this. I'm not distributing the file across all the computer resources, because each core is processing a different file. So in this particular case, I can compute 2.1 kilobits of data approximately across all the registers. Now, of course, one register is doing the \n. Some registers are going to be the \t to see if there's any tab characters. Some could be doing \r for return characters. So these all will take some form of the registers. So I technically might have 16 registers just for the data itself. It's still a lot, so it's around 1.6 kilobits of data that I can still process in one instruction cycle, or how many instruction cycles this instruction takes. So Intrinsics is the high level concept of what intrinsics are. So let's have a look at the code. So you technically include the intrinsic.h. I am using the Intel compiler for all of this. I'm not using the GCC compiler. Intel compilers are optimized for the Intel platform. And in here, there's the 512 instructions. This is technically saying I am trying to first load all the data, which is my string, into one of the registers. So that will be one of my registers over here. And before I do that, I want to load all my registers with these characters that I do not want in my string. So I want to remove spaces. I want to remove \n, \t, \r, This is all. It's all part of the trimming part of it, removing all the white spaces and normalizing my data. And once I've set all of these registers with the things that I want to compare with, then I load my text into this. And once I load my text into this, I am doing the computation. I am doing something called as compare and equal to. So I'm seeing whether it compares and equals to any or one of these characters, and if it compares to one of these characters, then I remove it from the string, and then I normalize the string and clean up the string. So this whole thing can be computed at a very high speed, because now I'm leveraging Intrinsics, and Intrinsics allows me to parallel process at this very granular level, at the register level, something that's not, you know, it kind of seems difficult to do, but it's really not that difficult once you start to play around and get a feel of what Intrinsics do. Now that we've gone through a little bit of the theory of what's going on under the hood, now let's start to like run the program, and from there we'll start to break down a little bit of the code to get a feel of what's going on under the hood. So let me take you to one of my compute resources that's there, where I've got access to the 2 Xeon processors to do this right now. You can also use the Intel Cloud platforms to do this, but currently where I work, we have some form of resources that I can do this with. So let's have a look at how we can leverage all of these parallel computing concepts that I just spoke about in our application. So in here, I am currently in my MPU in my cloud computing platform right now over here. And what I want to do is, I just want to show you that where I am right now is I have my application running right now, and I'm going to run this program. As I mentioned earlier, MPI Run allows us to MPI run the program, and here I'm putting all my debug statements on because I want to see what's going on. And in this particular case, I'm saying I want to bind it to the 2 sockets, because you can bind it per core. Currently, it's not set up to bind to multiple compute resources across different nodes. But in this particular computer, we have 2 different CPUs. So I can have a look at, you know, how I want to distribute my MPI process. So I'm saying please bind it one CPU, one socket will run one program, and the other socket will run the other program. NP is the number of processes to spawn, so I'm spawning 2 processes. And in this particular case, I'm saying you process one of the process will produce process. One of the processors will compute one data, and the other process will compute the other data, and one is to print the output. So when I run this thing, it will load the system, load the application, and it'll take all the data, bring it into DRAM, process everything, and it's processing around 2,000 files, and it's around like 200 MB of data. It's not a lot, but the processing and computation of string manipulation, string cleaning can take a lot of time, and it's already done. There are some memory leaks that I will clean up shortly, but nevertheless, that's the speed you can get when you hyper optimize for everything. So let's have a look at a little bit of the code. I'm just going to use this, and I'm just going to go to the main program. So in the main program that we have over here, I am using GCC. I'm not using GCC, I'm using C code to do the whole programming. And here I initialize all my MPI initialization. I'm saying, let me know what's the rank of my current process and what's the size. So rank is, if you spawn 2 processes, then it'll tell you each one will have its own rank. So you want to know what rank it is amongst, say 4 processes. I want to know what rank I am as the processor that's running, as a process that's running. And what's the total size of all the MPI in the world? In the sense, if you're spawning 2 processes, then the size will be 2. If you're spawning 4 processes, your size will be 4. And in there, where am I in that 4 processes that has been spawned? And here we do some form of affinity, as I mentioned, the NUMA affinity, to say, wherever the process is running, I want you to bind all my memory to this particular socket, which is the closest to the socket. And here we get the number of threads that each socket has. So I want to know whether I'm able to distribute my application across all the threads or all the cores. And here we say, if you're rank 0, then you process only this type of data. And if you're not ranked 0, then you process this type of data. And at the end, you just print out, hello world, I am from this rank. So that's the high level overview of the main file, what it's doing at this level. So now let's break the code down a little bit more further to see what's happening when we process, say, the process X. Now in this file, when we process the X, we are now loading everything into DRAM first. So we're loading all the data. And then once we load all the data, we're now going to process each of the files in different cores. So here we do something called as pragma OpenMP parallel for schedule dynamic 1. So in this particular case, we're saying schedule 1 one file at the time and do it dynamically. So dynamic means load balancing, which means that if the thread is finished completing the process or the task, then take the next data that it can process. And here I'm just doing some print statements of saying, how many threads are running, which thread is processing which file. And then we do the extract section from memory, which is going to do the XML parsing, which is going to clean up all the data. So that's where the OpenMP does, which is distributing across all the threads for that particular socket. Now let's go and look at how the intrinsics work. So this file is, taking all the data and parsing all the XML. The data is in XML, and we're trying to go through the loops of, cleaning up all the data. And we go through each section, and each section now needs to be cleaned up, and we got to trim it. And once it's trimmed, we then can save it into create the embeddings and save it into the database. So here is where I use the trim and normalize white space. So here we want to clean up all the data because the data is not very clean. It's got a lot of white space. It's not well formatted, and we want to remove anything that's not necessary. That's not going to help the whole. It's not going. The AI is. We want to train the AI in such a way that we're cleaning up all the data, and that's an important part. So in this particular case, I am now using this function called trim and normalize white space. As I mentioned earlier, this is all the white space I want to remove, and because I have the AVX512 instruction set, I can utilize the AVX512 instruction set. And when I do this, I am loading each one in each register. It's a one-to-one mapping with the actual assembly and register. So though it's in C, it's it's technically kind of like writing in assembly, because it also doesn't. It looks very little bit more cryptic, but it's not that difficult to understand, and that's the beauty about this. And then you load the data into this particular register, and then you're comparing whether each one of this text or each one of this character has any of these white spaces. And if it does have a white space, you then process it in terms of either removing it or you keeping it, and vice versa. And once after all of it is done, and if they do not fit in the 64 bytes of that register, then you say whatever is remaining, you process it after that. And then we start to once everything is done, then we can print out the data. So at the end of the year, it's processed everything, and then we just print out a number of sections, how it's all cleaned up, and all that cool stuff. So that's pretty much it in terms of the code. And if you wanted to have a deeper look at how this particular CPU is configured, you can have a look over here, and it shows the full topology of how the CPU is connected. So we have two CPUs over here, and each CPU has a couple of cores. So each one has around 7 cores, and 7 cores, it's around 8 cores. 0 to 7 is 8, and each core has 2 threads, so that's around 16 cores in this particular case. And you can parallelize for this socket, and similarly over here. And you also have L1, L2, L3 cache. L1 cache is 32 kilobits, and L2 cache is around around 1 MB, and L3 cache is around 25 MB. And L3 cache is generally common to all the cores and threads, but L1, L2 is specific to the core and the thread for that particular core. And know what instructions you have in your system, you can do the lscpus command, which will tell you what all instruction sets you have. And in this particular case, we have all the AVX512 instruction sets that you can see over AVX512F for floating point, AVX512 for DQ. AVX512 is just the instruction name, but in many other formats that it can, special that you want that it needs to be handled. In terms of your VNNI is a neural network interface, so it can do some form of convolution neural network in this particular instruction set. So depending on what you have, that kind of data can be processed. So it can process data in bfloat16, convolution neural networks, and many other things. So you can see over here that it has different AVX512 instruction sets, and accordingly you need to compile it with those flags. So let's have a look at what the flags look like. So if I do a cat dot so in my make file, which I'm using CMake right now, here I'm trying to say first and foremost use the ICC compiler, which is the Intel compiler. And if not, then you use the GCC compiler, but try to use the Intel compiler because we're using the Intel platform. But if I port this code to AMD, then perhaps, AMD could work. There I'm saying, please check whether the MPI packages are out there. Please check whether we have libxml because we're parsing libxml. Check whether we have the NUMA affinity NUMA controls because we want to, have the memory affinity. And once everything is all the libraries are installed, then we pass in certain flags. And some of the flags that we are passing over here is we're passing the AVX512 float flag, the AVXBW flag, and we're telling it, to process, give us the warnings and spit out every certain things. And we're also asking to process the OpenMP. And then there is other things that we can ask for in terms of, whether if it's Intel or Clang or whatever be it. We want to sanitize the address so that, we can see whether there's any memory leaks and stuff like that. So this is a very simple CMake file that allows us to compile it. It'll generate the make file and then we can compile it. And that's really it. In terms of, what the application is. There's a lot of components, a lot of pieces happening together, and this is the kind of code that you would write for high performance compute, and then you would distribute this across all the different computes and all the different nodes. This is very important when you're doing AI training, when you have a forward pass and then you have a backward pass, and you're training it across thousands and millions and trillions of data set, as we can see in the applications that are really performant and are available to us. They're training it across trillions of data sets. And how do you distribute this compute across all of these computes? And this is the kind of code you would write in a nutshell. Now, of course, you would use GPUs because GPUs would have a lot more cores, and accelerators would have a lot more cores. But the main concept is the same thing. Now, you would, instead of doing everything through a CPU, you would offload it to a GPU. But in the same way, you would still have to think of parallel processing. It's going to be a single instruction, multiple data. In many cases, they call it single instruction, multiple thread. But the idea is the same thing. The thinking is the same thing. And what I'm trying to show you over here is the idea of what it takes to become and write parallel programming compared to just writing, a program that just runs across, one single thread. And so it's more serial, whereas this is a little bit more, you got to think about, how am I going to put what where? And it's kind of more of like a creativity thing once you understand the science behind it. So that's really it. I thought it was a very cool exercise. And if you want to know more about these videos, more about HPC and high performance compute, please, comment below. I'm really interested in developing my knowledge. I'm also thinking of, perhaps investing in a small HPC cluster, get some few, Xeon processors, and start to show how you orchestrate with the HPC compute. If that's something that interests you guys, I'll be more than happy to invest and and demonstrate how you can actually set up your own HPC cluster, especially now when we're in a time where AI is such a dominant thing that high performance compute is becoming more and more relevant. Not to mention the top even job postings on OpenAI, at least at the time of this recording, is HPC compute, and those are future jobs. So HPC skill sets is becoming more and more relevant due to the applications that are now starting to showcase, in 2024 and beyond. So I hope you like this video. Do like it, do comment. If you want to know more about this, do comment below. And if you want to get more into the, me investing in more into designing my own HPC clusters, that will be, just give me a thumbs up, and I will be more than excited to showcase how it's done. Until next time, please take care.